Right, so starting polygons. And a polygon is a plane figure that's formed by 3 or more segments called sides, such that no 2 sides with a common endpoint are collinear, and each side intersects exactly 2 other sides. So you have to have at least 3 sides, because it's got to be a closed figure. Right, 2 sides would only make an angle that would be open. And it's made up of line segments. So let's test our knowledge. A polygon with 3 sides would be called a what? Triangle? How about 4 sides?
Square. Rectangle.
Those are in the right category, but that's not what we call it.
Quadrilateral.
Quadrilateral. About 5 sides.
Hexagon.
6 would be a hexagon. Correct. 7.
Set.
Heptagon. 8. Octagon. 9. Always gets slower to answer at this point. Nonagon. 10. Decagon. 12. Anybody know 12? It is a dodecagon. And then once we get past 12, 13, 14, 15, we just take the number, whatever that is, what the n represents, and put gon after it. So you have a 13 gon, 17 gon, 21 gon, so forth and so on. All right. So when we're looking at polygons, there are some other descriptors that can go along with it. One is we can call it convex or concave. Convex is going to be a polygon with no lines that contain a point in the interior of the polygon. And concave is a polygon that is not convex. So if none of the lines go into the interior, it's convex. If any go in the interior, it's concave. So if we have a polygon, what that means is if I take the segments that make the sides and I extend those out, if it's convex, all of those extensions are going to be on the outside of the figure. They're going to go to the outside. A concave polygon would be something more like this, where if I extend some of those sides, they're going to go into the interior of the polygon. Right? So if the extended sides all go on the outside, it's convex. If they go on the inside, it's concave. Right? You can think of going inside of a cave, or think of things caving in, which means they fall into the inside. And then a regular polygon is going to be a polygon that is equilateral and equiangular. So all the sides are going to be the same length, and then all the angles will be the same measure. Now we get to some theorems that will allow us to do calculations with these polygons. First, you got theorem 6.1, the interior angles of a quadrilateral theorem, which basically just tells us that the interior angles add up to 360 degrees. All right, so all the interior angles add up to 360 if it's a quadrilateral. If it's another polygon, then we can use the polygon interior angles theorem to figure out what the interior angles add up to be. So we use the formula n minus 2 times 180. So n represents the number of sides. So take the number of sides, subtract 2 from it, and then multiply by 180. And that'll give us the total sum of the angles, which, like here, we've got a square, 4 sides. So 4 minus 2. So the number of sides minus 2, which is going to be 2 times 180, would give us 360, which is what the interior angles of a quadrilateral theorem tells us. They add up to 360. Another one that we already knew, but that we can plug into the formula and still see that it works, is a triangle. 3 sides. So 3 minus 2 times 180, or 1 times 180, gives us 180 degrees for the interior angles of a triangle. So it works no matter how many sides it has. We can figure out what the measure of the angles add up to be. Corollary to theorem 11.1, the measure of each interior angle of a regular polygon. So regular, remember, it's got to be equilateral and equiangular, otherwise you can't use this formula. But basically all it is this formula up here, n minus 2 times 180, and then we divide it by the number of sides. So n minus 2 times 180 divided by n. So if I have a figure like a pentagon, assume that's regular, that all the sides and all the angles look the same. Right, so if I wanted to figure out what the measure of one interior angle would be, I would use n minus 2 times 180 divided by the n. So the number of sides is what n is, so a pentagon is going to have 5 sides, so 5 minus 2 times 180 divided by 5, when we plug in 5 for the number of sides. It's going to be 3 times 180 divided by 5, which 3 times 180 would be 540 divided by 5 is going to be 108. So each one of the angles of a regular pentagon would be 108 degrees. All right, theorem 11.2, the polygon exterior angles theorem, tells us the sum of the measures of the exterior angles of a convex polygon, one angle at each vertex, is 360 degrees. So if I have a regular polygon like this pentagon, and I extend each side out so that I create one exterior angle at each vertex, then all 5 of those angles added together are going to equal 360 degrees. And it doesn't matter how many sides it has, it will always add up to 360 on the exterior angles. So corollary 11.2, the measure of each exterior angle of a regular polygon is 1 over n times 360, or 360 divided by n, the number of sides. So if I wanted to know the measure of one of those angles, that's going to be 360 divided by the number of sides, which is 5, or 72 degrees would be the measure of each angle there for the exterior angles. All right, so this next group, we're determining if the following polygons, if they're a polygon, we're going to name what kind of polygon it is, then determine whether it's regular, concave, or convex. So the first one, top left, is that a polygon? Closed figure made up of segments. And so it is a polygon. What kind of polygon is it? First off, based on the number of sides, it's what? So it's a triangle. And I heard that it's convex. All right, so if I extended the sides, all those extensions go on the outside. They don't go into the interior. Is it a regular polygon? Remember, regular means that the sides are all the same length and the angles are all the same. Which when we look at it, looks like a right triangle, so there's no way the other two angles are going to be right angles as well. So it's not regular. So it's just a convex triangle. You can't say that it's regular here. How about this next figure? Is that a polygon? Is it a closed figure made up of line segments? Is this a line segment right here? If I'm going to draw a line, do we usually make it look like this? No. So that would not be part of a line either. It's more like part of a circle, right? And so if it was a polygon, we might call it a snowconagon, but it's not a polygon. All right. So it's not a polygon. Or maybe we could call it a notagon. All right. All right, so next one, is that a polygon? And what kind of polygon would it be? Got 6 sides, making it a hexagon. Is it regular? All the sides, all the angles are all marked congruent, right? So it would be regular. How about concave or convex? Convex. If I extend all those sides, they're all going to stay on the outside. Next one there below the triangle. That is a quadrilateral, 4 sides. Is it regular? Sides and angles are all marked congruent. And concave or convex? All right, so then the next one there to the right. Looks like an arrow. Would that be a polygon? So it is a polygon. What kind of polygon would it be? It's got how many sides? 7, so it is a heptagon. And then it's got a couple of things marked congruent, but everything is not marked congruent. All the sides aren't marked congruent. So it's not regular, but is it concave or convex? So this one would be concave. Where if I extended the sides on the inside there, they would go on into the inside. All right, so the next one there. It's got 5 sides, so it would be a the sides are marked congruent, but we don't know about the angles, so we can't say that it's a regular polygon. But is it concave or convex? Convex. All right, so then next one down here, y'all don't have on your sheet because I printed these off of what I had in my file and forgot that I updated this last year. So you got a star here with all made up of all segments, so it would be a polygon. And what would we call that polygon? It is a decagon. 5 points to the star. Each point's made up of 2 sides, so that's 10 sides. So a decagon. All the sides are congruent, but there are no congruent angles, or not all of the angles are congruent there. So we can't say that it's regular. Is it concave or convex? concave. And that check mark there to the right, would that make a polygon? What kind of polygon would it be? Hexagon, 6 sides. And nothing's marked congruent, so we can't say that it's regular, but it is concave. These sides right here on the inside will go to the inside. All right, so then this last section, solving for x. So first thing we got to do is figure out all these angles are marked. The x's are in 2 of the angles. So in order to figure out what those x's are, we've got to know what the total is for all of the interior angles, what they should all add up to. And since this has 1, 2, 3, 4 sides, that fits in with the interior angles of a quadrilateral theorem, which says that those angles add up to 360 degrees. So we know all 4 of these angles have to add up to 360 to solve for x. We're going to add them together. 3x plus 2 plus 2x plus 5 plus 88 plus 97. It's going to have to add up to 360. So then it's just a matter of solving the algebra problem. So 3x plus 2x is 5x. 2 plus 5 is 7. 7 plus 88 is 95. 95 plus 97, 192 equals 360. And subtract the 192 from both sides. Give us 5x equals 168. And divide by 5. So x is going to be 33.6. Then this next one to the right, the x is on an exterior angle. It's on the outside of the figure. And so we have to remember what we learned up here at the top of this page, which says that the sum of the measures of the exterior angles of a convex polygon, one angle at each vertex, is 360 degrees. Or the measure of one exterior angle is 360 degrees divided by n. So this one angle, that 2x, is going to be equal to 360 degrees divided by the number of sides. How many sides does it have? 6. So it's a hexagon. So 2x equals 360 divided by 6. Or 2x is going to equal 60. And then lastly, divide by the 2. So the value of x is going to be 30 there. And the last one here, we have a 5-sided polygon, or a pentagon. And we're trying to solve for this one angle right here. So once again, we have to know what all the angles have to add up to be before we can solve for the x. So we're going to use n minus 2 times 180 to find the sum of the interior angles. So n in this case is 5. So 5 minus 2 times 180, or 3 times 180. So it'll be 540 degrees for the sum of all those angles. So now all those angles added together have to equal 540. So x plus 114 plus 105 plus 102 plus 135. All 5 angles add together have to equal 540. So x plus, add up all those angle measures, 114 plus 105 is 219, plus 102 is 321, plus 135 is 456. And subtract 456 from both sides. So that x is going to be 84.